There is a part of the ocean where sunlight has never reached, not once in the entire history of the Earth, a region that begins far below the surface and continues downward into a depth that grows colder, darker, and more unfamiliar with every passing meter. For most of human history, it seemed obvious that nothing could live there. Without light, there could be no plants, no energy, no foundation for life as we understood it, and so the deep ocean was imagined as a vast, empty space, silent and still. That assumption held for a long time, until, in 1977, a small expedition descended into the deep Pacific and found something that did not fit that expectation at all. Not emptiness, but life. Not scattered or struggling, but active, organized, and sustained in ways that did not rely on sunlight in any recognizable form. What was discovered there forced a reconsideration, not just of the ocean, but of the conditions life itself requires. And what makes it more difficult to fully grasp is that this was not an isolated discovery. Each time we return to those depths, even briefly, something new appears. Unfamiliar forms, unusual behaviors, creatures that seem to operate under a different set of constraints, in an environment where energy is limited, time stretches, and survival depends on opportunities that may not come often. Most of this world remains unseen, not because we have ignored it, but because reaching it is one challenge, and remaining there long enough to understand it is another entirely. And the deeper we try to go, the more that limitation becomes clear. Tonight, we move slowly into that darkness and take a closer look at the part of the ocean where life continues without sunlight, and where each observation reveals just how much remains beyond our reach. If this kind of slow journey into the unknown is what you come here for, a like and a subscription help us keep going, and they mean more than you might think. Now, let's go down. It does not begin as a sudden boundary, but as a gradual surrender. The water darkens by degrees, the last traces of surface brightness thinning into a dim suspended haze until even that faint glow begins to dissolve. This is where the midnight zone takes shape, not as a line, but as a slow transition that deepens with every meter, drawing the ocean away from the influence of the sun. Above, there had still been a lingering softness, a suggestion of light filtering down through layers of water. Here, that suggestion fades. The descent passes through what is often called the twilight zone, a region where sunlight still arrives, but only in weakened fragments. Colors lose their clarity first. Reds disappear, then oranges, then yellows, until everything settles into shades of blue and gray. Even these tones grow dull, as if the water itself is absorbing what remains. By the time this transition completes, usually around 1,000 meters below the surface, sunlight no longer reaches at all. Not dim, not scattered, not even in the faintest measurable trace. The ocean becomes fully dark, not in the way night feels near land, but in a deeper, more complete absence, where light has no presence to begin with. The reason for this disappearance lies in the nature of water itself. Sunlight, though it appears strong at the surface, weakens rapidly as it travels downward. Each wavelength is absorbed at a different rate, stripped away layer by layer. Water molecules, along with particles suspended within them, scatter and absorb the energy, converting it into heat or redirecting it into paths that never continue downward. What begins as a broad spectrum of light becomes narrower, then thinner, until nothing remains to carry further. Distance plays its part as well. The ocean is vast in depth, and even the clearest water cannot transmit light indefinitely. The energy simply does not endure. By the time it has traveled far enough, it has already been diminished beyond usefulness, leaving the lower layers in permanent darkness. As the descent continues into this region, the change is not limited to light alone. Temperature drops steadily, settling near freezing, though the water never turns to ice under the immense pressure. That pressure increases with quiet persistence, rising by 1 atmosphere roughly every 10 meters. By the time the midnight zone is reached, the weight above becomes immense, compressing everything within it, shaping the very structure of the environment. These shifts do not occur slowly in a human sense. Moving downward, even at a controlled pace, the transformation feels swift. Within a relatively short vertical distance, the familiar conditions of the surface give way to something entirely different. Light vanishes, temperature stabilizes in cold stillness, and pressure builds into a constant, unseen force. There is no horizon here, no reference point to suggest scale or distance. Without light, space loses its usual meaning. Up and down remain, defined only by gravity and movement, but beyond that, the surroundings offer no visual guidance. The water extends outward in all directions, uninterrupted and uniform. This is where the midnight zone fully begins, not marked by a boundary that can be seen, but defined by what is no longer present. The sun, once the dominant force shaping life above, no longer has any influence here. What remains is an environment governed by different limits, where conditions are set not by cycles of day and night, but by depth, pressure, and the quiet persistence of the ocean itself. There is a point in the descent where the eyes continue to search, but nothing answers back. The last remaining glow has already faded behind, and without a clear moment of transition, the surroundings shift into something that offers no visual return. The absence settles quietly, not as a dramatic change, but as a condition that simply becomes complete. At first, the instinct is to adjust. Human vision is built to adapt, to widen its sensitivity, to gather what little light remains and shape it into form. In shallower depths, this works well enough. Shapes soften but remain present. Outlines blur yet still exist. Here, that effort continues for a time, the eyes straining gently, expecting detail to emerge if given a moment longer. But there is nothing to gather. No scattered photons remain to be collected, no faint reflections to assemble into meaning. The visual system, so reliable in every other environment, reaches a limit it cannot extend beyond. It does not fail abruptly, but it loses its purpose. The darkness is not something being looked through, it is something that offers no surface to interpret. Instruments carried into these depths often confirm what the senses already suggest. Even the most sensitive detectors register the absence, recording values that approach zero, where light no longer contributes to perception. What remains is a space that cannot be translated through sight, only occupied. For those descending in submersibles or specialized suits, this shift is understood in advance. Yet understanding does not fully prepare the mind for its effect. The human brain expects continuity, a world that can be mapped visually, even if only faintly. When that expectation is removed, orientation becomes something else entirely. Up and down remain known through movement and reference, but the surrounding space offers no confirmation. In such conditions, vision becomes secondary to other forms of awareness. The subtle hum of equipment, the gentle feedback of motion through water, the awareness of depth through instrumentation, these begin to replace the role that sight once held. The environment is no longer observed in the usual sense, but inferred through a combination of signals that do not form images, only impressions. There is also a quiet psychological shift that accompanies this change. It does not arise from fear or alarm, but from the unfamiliarity of existing in a space where one of the primary senses no longer provides information. Even highly trained divers, accustomed to low visibility, encounter a difference here that cannot be bridged by experience alone. In murky water, there is always the sense that something could be seen if approached closely enough. In this depth, that possibility does not exist. Time begins to feel altered in subtle ways. Without visual markers, moments are not easily measured against changing surroundings. Movement does not produce the same feedback, and distance does not reveal itself through shifting perspective. The descent continues, but it does so without the usual cues that confirm progress. Yet within this absence, a different kind of awareness forms. It is quieter, less immediate, shaped by patience rather than reaction. The environment does not offer sudden changes or sharp contrasts. Instead, it holds steady, consistent in its lack of light, allowing the mind to adjust not by restoring vision, but by letting it recede. What remains is a state where presence is defined without sight, where the surroundings are understood not through images, but through the knowledge of being within them. The ocean, at this depth, does not reveal itself in the ways that are familiar above. It simply exists, complete in its darkness, unchanged by the absence of observation. Before anything else becomes visible, it is the light that appears. Not a glow that fills the surroundings, but a small, precise point suspended in the distance. It does not arrive from above or reflect from any surface. It exists on its own, self-contained, steady for a moment, then gone. Another follows somewhere else, faint and brief, like a signal that was never meant to be understood, only noticed. In this depth, light does not come from the sun. It is made. Bioluminescence becomes the primary source of illumination, produced through chemical reactions within living tissue. Specialized cells, often arranged in patterns along the body, combine molecules in a process that releases energy as visible light. It requires no external input, no stored sunlight, only the internal chemistry carried by the organism itself. The result is efficient and controlled, shaped by evolution into forms that serve specific purposes. Some lights pulse slowly, expanding and fading in measured intervals. Others flash in quick bursts, sharp and deliberate. There are glows that remain constant, outlining the shape of a body in dim blue or green, and there are signals so brief they leave only a memory of their presence. Each variation carries meaning, though not in a way that can be easily interpreted from the outside. In a place where vision once ceased to function, these lights create a new kind of visibility. Not a continuous landscape, but fragments of activity, appearing and disappearing without warning. The darkness remains dominant, yet it is no longer empty. It is punctuated, interrupted by movement that reveals itself only in flashes. The purposes behind these lights are varied, though they follow certain patterns shaped by necessity. Some creatures use them to draw others closer. A small glow, gentle and rhythmic, can suggest something harmless, something worth approaching. In an environment where food is scarce, such signals become invitations that conceal their intent. The distance between two organisms closes, guided by a light that seems safe, until it no longer is. Other lights serve to confuse. Sudden bursts can disorient, breaking the continuity of motion, making it difficult to track direction or form. A sequence of flashes may suggest multiple sources, scattering attention across empty space. In these moments, clarity dissolves, and the observer loses the ability to distinguish where one body ends and another begins. There are also those that use light to remain unseen. By producing illumination along the underside of their bodies, some creatures match the faint residual glow that filters down from above, blending into it. This form of counter-illumination erases their silhouette when viewed from below, allowing them to pass without detection. It is a subtle balance, requiring precise control of brightness and timing, adjusted to match an environment that offers almost nothing. As these lights move through the water, they create a shifting pattern that has no fixed reference. A glow appears, drifts slightly, then vanishes. Another emerges at a different distance, moving in a direction that cannot be easily traced. Without a continuous field of vision, these points do not connect into a larger picture. They remain isolated, each one complete in itself, yet part of a system that is always in motion. The effect is quiet, but persistent. The darkness is no longer absolute, yet it is never replaced. Light exists here as an event rather than a condition, something that happens briefly, then returns to absence. It reveals only what produces it, nothing beyond. In this way, the midnight zone carries its own form of illumination, not borrowed from the surface, but generated from within. Each small light marks the presence of life, moving through a space that would otherwise remain unseen, leaving behind no trace once it fades. Motion in this depth carries a cost that cannot be ignored. Every shift through the water requires energy, and energy is never abundant here. It does not flow freely or renew quickly. It arrives in uncertain intervals, scattered and infrequent, and so it is used with care. Movement becomes a decision rather than a habit, something measured against the quiet balance of survival. Many of the creatures that inhabit this region have adapted to this reality by choosing stillness over pursuit. They do not roam widely in search of food. Instead, they position themselves within the vastness and wait. Their bodies remain nearly motionless, suspended in the water or resting against unseen surfaces, conserving what little they have. In such an environment, the idea of chasing prey becomes less practical. There is no guarantee that movement will lead to a successful encounter. Each effort spent in motion risks yielding nothing in return. Over time, strategies that depend on constant activity fade away, replaced by approaches that rely on patience and precision. Ambush becomes the dominant method. A creature may remain in place for long periods, its presence barely distinguishable from the surrounding darkness. It does not need to see its prey in the traditional sense. Instead, it senses subtle changes, faint disturbances in the water, vibrations that travel slowly but persistently through the dense environment. These signals carry information about movement, direction, and proximity, allowing the waiting predator to build an awareness without relying on sight. When something approaches within range, the stillness ends, but only for a brief moment. The response is immediate and controlled, a sudden extension of the body, a rapid opening, a movement that lasts only as long as necessary. There is no prolonged chase, no extended struggle across distance. The encounter is resolved in an instant, either successful or not, and then the stillness returns. This approach reduces uncertainty. Instead of searching across a vast and empty space, the predator allows the environment to bring opportunities closer. It becomes part of the surroundings, integrated into the slow rhythms of the deep, waiting for the rare alignment of position and timing. There are also variations within this strategy. Some creatures position themselves along pathways where movement is more likely to occur, areas where drifting organisms pass through with subtle regularity. Others make use of faint signals, small cues that encourage curiosity or draw attention, guiding potential prey into a closer range without requiring pursuit. These methods remain understated, aligned with the overall need to conserve energy while increasing the chance of contact. The absence of light shapes all of this behavior. Without continuous visibility, there is no advantage in speed across distance. What matters instead is the ability to respond quickly within a limited space. Reaction replaces endurance, precision replaces range. The environment favors those who can remain unnoticed until the exact moment action becomes necessary. Even the structure of the body reflects this balance. Muscles are often arranged to allow for sudden bursts rather than sustained movement, capable of generating force quickly, but not designed for long pursuits. This design supports the pattern of waiting, followed by brief, decisive motion, a cycle that repeats with long intervals of stillness in between. In this way, hunting becomes less about searching and more about being present at the right moment. The vastness of the ocean remains largely unchanged, quiet and unoccupied, while within it, small events unfold with careful timing. A single movement interrupts the stillness, then fades, leaving no trace beyond the continuation of the dark, where patience remains the most reliable strategy. From the front of its head, a single filament extends into the water, thin and flexible, moving with a slow and almost weightless drift. At its tip, a small structure glows, steady and controlled, a point of light held just far enough from the body to exist as something separate. It does not illuminate the surroundings, only itself, and in doing so, it becomes the focus of attention within an otherwise empty space. This is the anglerfish, shaped by the same constraints that define everything at this depth, yet refined into a form that turns stillness into a method. The filament, known as an elysium, supports the luminous tip called the esca, where bioluminescent bacteria live in quiet symbiosis. These microorganisms produce light continuously, sustained by the environment within the lure, while the fish regulates its exposure, adjusting the glow in subtle ways. The motion of the lure is minimal, guided by slight movements of the head or gentle currents that pass through the water. It does not swing widely or attract attention through speed. Instead, it drifts with a quiet consistency, suggesting the presence of something small, something alive, something that might be approached without caution. In a place where encounters are rare, even a faint signal can carry significance. The body of the anglerfish remains still, while this light continues its slow, deliberate display. Its mouth, disproportionately large, waits just behind the lure, lined with inward curving teeth that allow entry but resist escape. The entire structure is arranged so that the space between lure and jaws becomes a narrow corridor, one that closes instantly when crossed. There is no need for pursuit. The anglerfish does not expend energy searching across distances or reacting to movement far away. It allows the environment to deliver opportunity directly toward it, guided by the suggestion created by its own light. This approach reduces the uncertainty that defines most encounters in the deep, replacing it with a controlled interaction that unfolds within a limited range. Energy efficiency is central to this design. The production of light through symbiotic bacteria requires little from the host once established, and the physical movement involved in maintaining the lure is minimal. Long periods can pass without action, the fish conserving its resources while the lure continues to function as a constant signal. When a response does occur, it is brief and decisive, lasting only a moment before stillness returns. This balance between inactivity and precision aligns closely with the scarcity of the environment. Food does not appear regularly, and the cost of missing an opportunity is significant. By transforming the act of hunting into a passive system that invites rather than pursues, the anglerfish increases the likelihood that each encounter results in success. The effectiveness of this strategy also lies in its simplicity. There is no need for complex tracking or extended movement. The lure presents a clear point of focus, drawing attention inward, while the rest of the body remains concealed in the surrounding darkness. The prey, guided by a single visible element, moves closer without perceiving the structure that waits behind it. Over time, This method has shaped the anglerfish into a form where every feature supports the same purpose. The extended filament, the controlled light, the expansive jaws, and the minimal movement all contribute to a system that functions with quiet consistency. It is not a display of speed or strength, but of alignment with the conditions of the deep, where efficiency and patience define what endures. Nothing arrives on a schedule here. There is no pattern that can be followed, no reliable cycle that brings nourishment at predictable intervals. The water holds life, but it is spread thin across an immense space, and encounters between organisms occur without warning. A creature may drift through this environment for long stretches without crossing paths with anything it can consume, sustained only by what it has already stored within itself. This unpredictability shapes every aspect of survival. Food is not something that can be searched for with confidence. It appears rarely, often by chance, carried along by currents, or guided by movements that cannot be anticipated. The distance between one opportunity and the next is not measured in simple units of time, but in the endurance of the organism waiting for it. Because of this, feeding becomes an event rather than a routine. When it happens, it must be enough to support long periods that follow without any guarantee of repetition. The body adapts to this rhythm by shifting its internal processes. Metabolism slows, reducing the rate at which energy is consumed. Systems that would require constant replenishment are minimized, allowing the organism to extend the usefulness of each meal far beyond what would be possible in more abundant environments. Energy storage plays a central role in this balance. Lipids accumulate within tissues, acting as reserves that can be drawn upon gradually. These stores are not used quickly, but released in small amounts over extended periods, maintaining basic functions while conserving as much as possible. The body becomes a reservoir designed not for immediate consumption, but for careful distribution across uncertain time. There are also behavioral adaptations that reflect this scarcity. Many creatures avoid unnecessary movement, reducing the likelihood of wasting energy on actions that may not lead to food. They remain in areas where the chance of encounter, however small, is slightly higher, allowing the environment to bring what it will rather than seeking it out actively. This approach aligns with the wider pattern of stillness, where patience becomes more effective than effort. The digestive process itself adjusts to these conditions. Some species are capable of processing large meals slowly, extending the extraction of nutrients over time. Others can pause digestion entirely, preserving partially consumed food until it is needed again. These mechanisms ensure that nothing is wasted, that each rare intake is used to its fullest extent. Uncertainty also influences physical structure. Bodies are often built to endure, with systems that can tolerate fluctuations in available energy without immediate decline. Growth may occur slowly, spread across long spans, reducing the demand for constant intake. Reproduction, when it occurs, is timed and adapted to these same limitations, ensuring that it does not depend on conditions that cannot be guaranteed. Even at the smallest scales, this pattern continues. Microorganisms drifting through the water follow similar constraints, consuming what they encounter and persisting through intervals where nothing new appears. The entire system operates within the same framework of scarcity, where availability is inconsistent and survival depends on flexibility rather than abundance. In this environment, the absence of food is not an interruption, but a normal condition. The rare moments of feeding stand out against long periods of waiting, each one extending the thread of survival a little further. Life continues not by securing constant access to energy, but by adapting to its absence, shaping itself around the expectation that what is needed may not come again for some time. In this depth, recognition comes second to response. When something enters reach, there is little time to evaluate its nature in detail. Form is often indistinct, movement brief, and opportunity uncertain. The organism that waits cannot rely on careful selection because the conditions do not allow for repeated chances. What appears may not appear again, and so the act of feeding becomes immediate, shaped by necessity rather than preference. Diet, in this environment, is defined by availability. Creatures consume what they encounter, regardless of whether it matches an ideal form. A passing body, a drifting fragment, even remains that have already begun to break apart, all become part of the same equation. The distinction between suitable and unsuitable narrows, guided less by choice and more by what can be physically managed. This lack of selectivity is not a limitation, but an adaptation. Systems within the body are structured to process a wide range of materials, extracting usable energy from sources that might be ignored elsewhere. Digestive mechanisms adjust to variability, capable of handling differences in composition, density, and condition without requiring specialization for a single type of food. There is also an urgency embedded in this approach. When an encounter occurs, hesitation introduces risk. The moment of contact is often brief, and delay can allow the opportunity to pass beyond reach. In the surrounding darkness, another organism may intercept it, or it may drift away into the vast space where it will not be recovered. Acting quickly increases the likelihood that the energy contained within that encounter becomes available rather than lost. This immediacy is reflected in behavior. Movements that accompany feeding are direct and efficient, minimizing the time between detection and consumption. There is little refinement in the process, no extended manipulation or inspection. The objective is to secure the resource before it disappears, ensuring that the rare arrival contributes to survival. At times, this leads to interactions that would seem imprecise in other environments. Objects that resemble prey may be taken without full confirmation, and substances that offer limited value may still be consumed. The cost of occasional inefficiency is outweighed by the benefit of capturing what is available when it appears. Over time, this balance supports persistence, allowing organisms to endure within a system that does not reward careful discrimination. The surrounding community follows similar patterns, creating a network of opportunistic feeding that extends across many forms of life. When something enters this space, it becomes part of a chain of interactions, each participant responding according to the same underlying principle. Energy moves through the system in uneven steps, guided by chance encounters and immediate responses rather than stable pathways. Even at smaller scales, this pattern continues. Microorganisms attach to drifting particles, consuming what they can from surfaces that pass within reach. Larger creatures may follow these particles as well, not because they guarantee nourishment, but because they increase the probability of finding something to consume. The entire environment operates within this framework, where each moment of availability is used without delay. In this way, feeding becomes less about preference and more about readiness. The organism does not wait for the ideal form, but remains prepared to act when anything arrives. This readiness ensures that the rare presence of food is not overlooked, allowing life to continue within a space where abundance is not part of the design. The shape of the mouth does not always match the size of the body. In this depth, proportions shift in ways that seem inconsistent at first glance. A small form may carry an opening that appears too large, a structure that extends beyond what seems necessary for its frame. Yet this imbalance follows a precise logic, one that reflects the conditions where food is not encountered often, and each opportunity must be used to its fullest extent. Some creatures possess jaws that are not fixed in the rigid way seen closer to the surface. Instead, they are loosely connected, supported by flexible ligaments that allow them to open far wider than expected. The lower jaw can drop, the upper can shift, and the entire structure expands outward, creating a temporary space capable of enclosing something much larger than the creature itself. This expansion is not limited to the mouth. The stomach follows a similar design, composed of tissues that stretch without tearing, accommodating volumes that exceed the normal proportions of the body. When prey is captured, it is not processed in small portions or broken apart externally. It is taken whole, drawn inward through an opening that reshapes itself to allow passage. The act unfolds with a kind of quiet determination. The jaws extend, the body adjusts, and the prey is guided inward, sometimes slowly, sometimes with sudden motion, depending on the species. Once inside, the structure contracts, securing what has been taken and returning the outer form to its usual appearance, though now distended by what it contains. This ability allows for a feeding strategy that does not rely on frequent encounters. When something substantial appears, even if it exceeds the size of the predator, it can still be consumed. The energy gained from such an event can sustain the organism through long intervals that follow, reducing the need for repeated feeding in an environment where repetition cannot be assumed. There are risks associated with this approach. Consuming prey of significant size places strain on the body, stretching tissues to their limits and increasing vulnerability during the period of digestion. Movement becomes more difficult, and the organism may become more noticeable to others within the same space. Yet, these risks are balanced against the potential benefit, where a single successful intake can support survival over extended time. Digestion itself proceeds slowly, aligned with the overall pace of life at this depth. Enzymatic processes break down the contents gradually, releasing nutrients over a prolonged period. The body absorbs what it needs in measured steps, maintaining stability while the stored energy is converted into usable form. Nothing is rushed and nothing is wasted. This capacity to consume beyond apparent limits reflects a broader pattern of adaptation. The environment does not favor moderation in the same way as more abundant systems. Instead, it supports those that can take advantage of rare abundance when it appears, even if doing so requires temporary imbalance. The forms that carry these expandable structures do not seek excess for its own sake. They are shaped by necessity, designed to respond when conditions briefly allow. Their bodies become tools for capturing and storing opportunity, transforming a moment of availability into sustained existence. In this way, the boundaries of size lose some of their meaning. What matters is not the scale of the organism alone, but the flexibility of its design, the ability to extend beyond its usual limits when the moment arrives, and to return again to stillness, carrying within it the energy gathered from a single, decisive act. Along the edge of the mouth, the teeth extend far beyond what seems necessary, slender and elongated, arranged in a way that gives the impression of excess. They are often so large that the jaws cannot fully enclose them, leaving the tips exposed even when the mouth is at rest. In another environment, such proportions might interfere with movement or feeding, but here they serve a precise and essential function. These teeth are shaped like fine needles, narrow and sharply pointed, designed not for chewing or breaking apart food, but for holding it in place. When the jaws close, the teeth interlock or angle inward, creating a barrier that resists any attempt at escape. Prey that passes between them finds no clear path outward, only a narrowing space that guides it further inside. The structure reflects the nature of encounters at this depth. Opportunities to feed are limited, and each one carries significant importance. There is little margin for error once contact is made. A missed capture or an escape represents not just a lost meal, but the loss of an event that may not repeat for an extended period. As a result, the anatomy favors certainty over versatility, ensuring that once something is caught, it remains so. The length of the teeth also allows them to function before the jaws fully close. Even a partial movement can bring the tips into contact with prey, securing it long enough for the rest of the mouth to follow. This reduces the need for precise alignment during the initial moment of capture, increasing the likelihood that the interaction will succeed despite limited visibility and brief contact. Material composition plays a role as well. These teeth are often translucent or lightly pigmented, reducing their visibility in the surrounding environment. They do not reflect what little light may be present, nor do they create strong contrasts that could reveal the presence of the predator. Instead, they remain subtle until the moment they are used, blending into the form of the organism until function becomes necessary. The overall appearance, when observed from outside, can seem disproportionate, even exaggerated, yet this exaggeration is not without purpose. Each feature has been shaped by the same constraints that govern the entire environment, where efficiency is measured not by balance or symmetry, but by effectiveness in rare and decisive moments. There is also an element of durability in this design. The teeth must withstand the strain of holding struggling prey, sometimes for extended periods, without breaking or loosening. Their structure allows for slight flexibility, absorbing force without losing integrity, ensuring that they remain functional across repeated uses over the lifespan of the organism. This emphasis on retention rather than processing distinguishes these adaptations from those found in more resource-rich environments. There, teeth may be used to tear, grind, or break down food into smaller pieces. Here, the priority lies in securing what has been obtained, allowing digestion to occur later and without interference. The visual effect of these teeth, extending outward and inward at the same time, creates a form that appears almost static even when in motion. They define the outline of the mouth in a way that is immediately recognizable, yet their purpose is revealed only in action when their arrangement transforms from appearance into function. In this way, the teeth of the deep reflect a broader pattern, where form is shaped directly by necessity and where what seems excessive at first becomes precise when understood within the conditions that produced it. At this depth, solidity becomes less useful than it appears. The forms that move through these waters often seem incomplete at first glance, lacking the firmness and structure expected of bodies under such weight. Their outlines are soft, their surfaces yielding, as though they could not endure the immense pressure surrounding them. Yet this impression comes from expectations shaped by environments where resistance is necessary, where rigidity protects against force. Here, a different balance has emerged. Pressure increases steadily with depth, compressing anything that contains empty space or rigid boundaries. Structures that rely on internal cavities filled with gas would collapse quickly, unable to maintain their shape. In response, many deep-sea organisms have moved away from such designs entirely. Their bodies are composed largely of water and flexible tissues, materials that do not resist compression, but instead accommodate it. Because water itself is nearly incompressible, a body that matches its density experiences less internal stress. There is no sharp difference between the pressure inside and outside, no force trying to crush or distort the organism. Instead, the body remains in equilibrium with its surroundings, shaped by the same conditions rather than opposing them. This results in forms that appear delicate, sometimes almost transparent, with minimal skeletal support. Bones, when present, are often reduced or lightly mineralized, providing just enough structure for movement without creating rigid points of failure. Muscles are arranged to function within this softness, generating motion without relying on strong leverage or resistance. The absence of rigidity also allows for subtle flexibility in shape. As pressure varies slightly with movement, the body can adjust without damage, shifting in response to the surrounding forces. This adaptability reduces the risk of structural stress, allowing the organism to maintain integrity even as conditions change. Buoyancy is another factor influenced by this design. Without large, dense skeletal elements, many of these creatures achieve a near-neutral balance within the water. They do not need to expend energy maintaining their position, nor do they sink rapidly when inactive. This complements the broader pattern of conservation, where energy is preserved wherever possible. Internally, processes continue at a pace suited to these conditions. Cells operate under pressure that would disrupt more rigid systems, yet their composition allows them to function without interruption. Proteins and membranes are structured to remain stable, maintaining their roles despite the surrounding force. The entire organism becomes a system aligned with its environment rather than one that resists it. There is also an economy in this softness. Building and maintaining rigid structures requires resources, materials that must be gathered and processed. In a place where such resources are limited, reducing the need for them becomes advantageous. The body uses only what is necessary, avoiding excess that would offer little benefit under these conditions. From a distance, these forms may seem incomplete, as though they lack the strength expected of life. Yet their strength lies not in resistance, but in compatibility. They endure not by holding their shape against the pressure, but by allowing that pressure to pass through them without disruption. This approach reflects a broader principle within the deep. Survival does not depend on imposing structure onto the environment, but on aligning with it so closely that the distinction begins to fade. The body becomes an extension of the water itself, shaped by the same forces, moving within them without conflict, sustained by a design that appears fragile, yet remains entirely suited to the world it inhabits. Some bodies do not interrupt the space around them. They pass through the water without leaving a clear outline, their forms present but difficult to define. Edges soften until they seem to dissolve, and what remains is only a faint suggestion of structure, visible from certain angles and then gone again. In a place where visibility is already limited, this reduction of form becomes a quiet advantage. Transparency allows light, when it appears, to move through the body rather than reflect from it. There is no solid surface to catch illumination, no clear boundary that separates organism from surroundings. Even the brief flashes produced by other creatures travel across and through these tissues without revealing a distinct shape. The body becomes less an object and more a continuation of the water itself. Achieving this condition requires a particular arrangement of internal structures. Tissues must be composed in a way that minimizes scattering, aligning cellular components so that light can pass with minimal disruption. Pigmentation is reduced or absent, removing the colors that would otherwise absorb and reflect wavelengths. Organs are often arranged to limit contrast, sometimes compressed or positioned in ways that reduce their visibility from outside. This design does not make the organism completely invisible. Movement can still be detected, and slight distortions in the surrounding water may reveal presence. Yet these signals are subtle, often too faint to draw attention in an environment where stimuli are already scarce. The absence of a clear outline delays recognition, and in that delay, the organism gains time. In a system where encounters are infrequent, avoiding detection becomes as important as securing food. If a creature can pass unnoticed, it reduces the likelihood of becoming part of another organism's rare opportunity. Transparency serves this purpose without requiring energy expenditure, functioning continuously as long as the body maintains its structure. There is also a balance between invisibility and function. Complete transparency would limit the ability to perform certain biological processes, particularly those involving complex organs. As a result, many species adopt partial transparency, allowing essential structures to remain while minimizing their visibility as much as possible. The body becomes a compromise between clarity and necessity, shaped by the need to remain unseen without losing function. The effect changes depending on the direction of observation, from above or below, where even minimal light differences can reveal contrast. Transparency becomes especially effective. Without a defined silhouette, the organism blends into the surrounding gradients, making it difficult to distinguish from the water itself. From the side, slight distortions may still appear, but these are often brief and easily overlooked. Over time, this adaptation integrates into the broader patterns of the deep. Creatures drift past one another without recognition, their forms present yet unacknowledged. Encounters occur only when other signals, such as movement or proximity, become strong enough to overcome the absence of visual definition. The surrounding environment supports this strategy by offering little that would counter it. With no constant light source to reveal shape and no stable background against which to measure contrast, transparency remains effective across most conditions encountered at this depth. It does not rely on specific circumstances, but functions consistently within the prevailing absence. In this way, being unseen is not an active effort, but a condition built into the body itself. The organism does not hide in the traditional sense, but exists in a form that does not draw attention. It moves within the water as part of it, carrying its structure without announcing it, sustained by a design that allows presence without visibility. Color in this depth shifts away from appearance and becomes a function. Some bodies do not reflect what little light reaches them or passes nearby. Instead, they take it in almost entirely, leaving nothing to return to the surrounding water. When a brief glow crosses their surface, it does not reveal shape or contour. It disappears upon contact, as though the light itself has been quietly removed. This effect comes from skin that absorbs nearly all wavelengths it encounters. The surface is structured at a microscopic level to trap incoming light, guiding it into layers where it is scattered and retained rather than reflected outward. Pigments within these tissues, often densely concentrated, convert the energy into heat or disperse it internally, preventing any significant portion from returning. The result is a form of darkness that appears deeper than the environment around it. Even in a place where light is scarce, these organisms create a contrast not by brightness, but by absence. When viewed against the faint illumination produced by other creatures, their bodies register as voids, areas where light ceases rather than continues. This adaptation extends the concept of camouflage beyond transparency, where transparent bodies allow light to pass through. these absorbent surfaces eliminated entirely. Both approaches reduce visibility, but through opposite means. One blends by becoming part of the medium, the other by removing itself from the visual field. The advantage becomes clear during brief encounters. When a nearby organism produces light, whether through movement or communication, the surrounding space is momentarily revealed. In that instant, anything reflective would be outlined, its presence made clear by returning light. An absorbent surface, however, remains hidden within that illumination, offering no signal that can be detected easily. This form of concealment does not rely on stillness alone. Even when movement occurs, the lack of reflection minimizes the visual trace it leaves behind. Edges remain undefined, and motion does not create the same disturbances in visibility that would occur with more reflective bodies. The organism can pass through illuminated areas without becoming clearly visible, reducing the chance of recognition. There is also a consistency to this adaptation. It does not depend on matching specific patterns or colors, which would require adjustment as conditions change. Instead, it functions across all instances of light encountered at this depth. Any illumination, regardless of its source or intensity, is treated the same way, absorbed and contained. The development of such surfaces reflects a refinement of structure at scales too small to observe directly without assistance. Layers within the skin are arranged to maximize absorption, creating a complex interaction between material and light that results in a simple outcome. From the outside, it appears as uniform darkness, but within, it is the product of precise organization. In combination with the broader conditions of the deep, this adaptation contributes to an environment where visibility is reduced even further. Encounters become more dependent on proximity and non-visual cues as the ability to detect form through light diminishes. Organisms that possess this quality move within a space where they are less likely to be noticed, even when illumination briefly returns. The presence of such bodies adds another layer to the quiet complexity of the midnight zone. They do not announce themselves, nor do they rely on elaborate displays. Instead, they exist in a state where light offers no advantage to those who might observe them, maintaining a form that remains concealed not by blending into brightness, but by removing it entirely. In some forms, the face carries no trace of sight at all. Where eyes might be expected, there is only smooth tissue or a reduced structure that no longer gathers light. The surface remains unbroken or marked by small remnants that suggest a function once present but no longer maintained. These organisms move through their surroundings without relying on vision, shaped by conditions where light offers no consistent advantage. Over time, the absence of usable light has influenced the direction of development. Maintaining complex visual systems requires energy, both in the construction of the eye itself and in the continuous processing of information it provides. In an environment where such information is nearly non-existent, these costs no longer yield meaningful benefit. Gradually, across generations, the structures associated with sight become reduced, simplified, or entirely absent. This process does not occur abruptly. It unfolds slowly, with each step favoring efficiency over unused capacity. Cells that once formed lenses or light-sensitive tissues diminish, replaced by forms that require fewer resources to sustain. The nervous pathways dedicated to interpreting visual input become less prominent, their functions redistributed or removed. What remains is a body that has redirected its energy towards systems that provide more reliable information. The energy conserved through this reduction is not insignificant. In a place where every unit of energy must be used carefully, Eliminating an unnecessary system contributes directly to survival. Resources that would have supported vision are instead allocated to processes that maintain stability, movement, or other forms of perception better suited to the environment. Without sight, awareness of the surroundings depends on different signals. The water itself becomes a medium of information, carrying subtle disturbances that can be detected through specialized sensory structures. These may take the form of fine extensions along the body, sensitive to changes in pressure or movement. Even slight shifts in the flow can indicate the presence of another organism nearby, revealing direction and proximity without requiring visual confirmation. Chemical detection also plays a role. Dissolved substances travel through the water, creating gradients that can be followed or interpreted. These signals provide information about potential food sources, other members of the same species, or changes in the environment. The ability to sense these gradients allows for navigation and interaction without reliance on sight. In some cases, electrical sensitivity contributes to perception. Weak bioelectric fields generated by other organisms can be detected through specialized receptors, offering another layer of awareness. This form of detection operates continuously, unaffected by the absence of light, providing a steady stream of information about the immediate surroundings. These alternative systems do not replicate vision, but they do not need to. They offer a different way of understanding the environment, one that aligns with the conditions of the deep. Information arrives through contact with the water, through gradients and fields, through signals that are always present even when light is not. The resulting behavior reflects this shift. Movement is guided by these inputs, responses shaped by patterns that are not seen but sensed. Interactions occur without visual cues, relying instead on proximity and detection through other means. The environment is navigated through a network of signals that form a coherent picture, though it is not one that can be described in visual terms. In this way, the absence of eyes does not represent a loss, but a transition. The organism becomes attuned to forms of information that remain constant in its surroundings, allowing it to function effectively without a sense that no longer serves its purpose. The water itself carries every movement. Nothing travels quickly here, yet every shift leaves a trace that spreads outward in slow, expanding patterns. A fin moves somewhere beyond direct contact. A body changes direction. A small displacement forms, and the surrounding water responds. These responses move through the environment as subtle waves of pressure, reaching outward in all directions, carrying information without form or image. For many creatures, this becomes the primary way of understanding what exists nearby. Along their bodies are specialized sensory structures, often arranged in lines or clusters, tuned to detect even the faintest changes in pressure. These systems do not rely on sight, but instead interpret the motion of water itself, translating disturbance into awareness. When something moves, it creates a signature. The size, speed, and direction of that movement shape the pattern of pressure that follows. A slow drift produces a different signal than a sudden shift, and these differences can be distinguished with surprising precision. The organism does not see the source, but it perceives its presence through the way the water has been altered. This form of sensing is continuous, operating without interruption. There is no need to direct attention toward a particular point, no requirement to focus or adjust. The entire body becomes receptive, collecting information from all sides at once. The environment is not observed as a series of images, but as a field of subtle changes, each one carrying meaning. Pressure sensitivity extends beyond immediate movement. Variations in depth, currents, and even distant activity contribute to the overall pattern. The organism learns to interpret these layers, distinguishing between background conditions and new disturbances. This ability allows it to navigate without relying on visual landmarks, orienting itself through gradients and flows that remain stable over time. Navigation, in this context, becomes an act of following these patterns. A consistent current may guide direction, while changes in pressure indicate obstacles or open space. The absence of light does not prevent movement because the environment provides other forms of structure. These structures are not visible, but they are present in the behavior of the water itself. Some species enhance this perception through additional mechanisms. Fine extensions, such as elongated filaments or sensitive appendages, increase the surface area available for detection. These structures extend into the surrounding water, capturing disturbances that might otherwise pass unnoticed. They move gently with the currents, continuously sampling the environment. There is also a level of interpretation involved. The signals received are not random, but part of a system that can be learned and responded to. Over time, the organism associates certain patterns with specific outcomes, refining its responses based on experience. Movement becomes more precise, reactions more aligned with the nature of the disturbance. This method of sensing operates quietly, without producing its own signals. It does not reveal the presence of the organism to others, as it requires no emission of energy, only reception. In a place where remaining undetected can be as important as detecting others, this passive approach offers a clear advantage. The absence of sight, once adjusted to, does not limit awareness. Instead, it reshapes it into a form that matches the environment. Information arrives through contact with the medium itself, through shifts that are always occurring, whether noticed or not. The organism becomes part of this continuous exchange, receiving and responding to the subtle movements that define the space around it. In this way, the deep is not empty of signals, but filled with them, carried quietly through the water, forming a network of information that exists without light, yet remains fully present for those adapted to perceive it. Every movement leaves a trace within the body that must be repaid. Muscles contract, internal systems respond, and energy that has been carefully stored begins to diminish. In an environment where replenishment cannot be assumed, even small actions carry weight. What might seem insignificant in other parts of the ocean becomes a measurable expense here, one that shapes behavior in quiet but persistent ways. Energy, in this depth, is not simply a resource. It is the central measure of survival, influencing every decision, every adaptation, every form that continues to exist. Without a steady supply, organisms must rely on what they already possess, stretching each reserve across uncertain spans of time. The balance between use and preservation becomes precise, guided by the understanding that excess cannot be replaced easily. This constraint leads to a noticeable pattern. Many creatures move very little, not because they lack the ability, but because restraint offers a greater advantage. They remain suspended or settled, their bodies aligned with the surrounding water, reducing the need for active propulsion. Motion is reserved for moments that require it, brief and purposeful, followed by extended periods of stillness. Drifting becomes a strategy rather than a passive state. By allowing currents to carry them, organisms can change position without expending energy. The water provides movement without cost, transporting them through different regions where the likelihood of encountering food may shift slightly. This passive relocation replaces the need for active searching, aligning with the broader pattern of conservation. To support this approach, bodies are often structured to maintain balance within the water column. Density is adjusted so that sinking or rising occurs slowly, if at all. Some species develop internal compositions that match the surrounding fluid closely, allowing them to remain suspended with minimal effort. Others use subtle adjustments, small changes in orientation or internal pressure, to maintain position without continuous movement. Even when movement occurs, it is often reduced to the smallest necessary action: a gentle flick, a slight contraction, just enough to alter direction or respond to a nearby signal. There is no excess in these motions, no extended pursuit or rapid change unless it becomes essential. The body operates within a narrow range of activity, conserving strength for moments when it cannot be avoided. This restraint extends to the internal processes as well. Metabolic rates remain low, reducing the demand for energy across all systems. Growth slows, reactions become measured, and the overall pace of life aligns with the limited availability of resources. The organism does not attempt to exceed these limits, but adapts to them, maintaining function within a controlled range. The surrounding environment supports this stillness. Without strong currents or frequent disturbances, the water remains relatively stable, allowing organisms to hold position without constant adjustment. This stability reinforces the effectiveness of drifting and minimal movement, creating conditions where energy can be conserved without compromising survival. Over time, this pattern becomes a defining feature of life at this depth. Movement is not absent, but it is selective, shaped by necessity rather than impulse. The body remains prepared to act, yet chooses not to unless the situation demands it. In this balance, energy is preserved, extending the duration of survival in a place where renewal is uncertain. Within this quiet system, drifting is not a loss of control, but a deliberate alignment with the environment. The organism moves with the water rather than against it, conserving what it has while remaining open to what may come, sustained by a strategy that values stillness as much as action. Time in this depth does not pass in the same way it does above. Changes unfold gradually, often beyond immediate perception, shaped by a pace that reflects the limited flow of energy through the environment. Nothing moves quickly unless it must, and even then, the moment is brief, followed by long stretches where activity returns to stillness. Within this rhythm, life adjusts not by accelerating, but by slowing almost everything it does. Metabolism becomes reduced to a steady minimum. The chemical processes that sustain the body operate at lower rates, consuming less energy over time. Cells divide more slowly, reactions proceed with measured precision, and the overall demand placed on internal systems decreases. This reduction allows organisms to extend the usefulness of each resource they obtain, maintaining function without requiring constant replenishment. Growth follows a similar pattern. Instead of rapid development, bodies expand over extended periods, sometimes taking years to reach forms that would emerge more quickly in other environments. Each stage of growth is supported by limited input, and so it progresses only as conditions allow. There is no pressure to reach maturity quickly, because the environment does not favor speed in this regard. Reactions, too, become less immediate. When a stimulus is detected, the response may be delayed, not from inefficiency, but from a system calibrated to conserve energy. Sudden movements are rare, reserved for moments where they are necessary. In most cases, adjustments occur gradually, aligning with the slow pace that defines the surroundings. This reduction in speed does not hinder survival. In fact, it supports it. Rapid movement and quick reactions require energy that is not readily available. Attempting to maintain such activity would deplete reserves without guarantee of benefit. By slowing down, organisms remain within the limits imposed by their environment, ensuring that their energy use remains sustainable over time. The interactions between organisms reflect this pacing. Encounters unfold without urgency, movements measured and deliberate. Even processes such as feeding and digestion extend across longer intervals, aligning with the reduced metabolic rate. The entire system operates within a framework where time stretches, allowing life to continue without the need for constant acceleration. Longevity often increases under these conditions. With slower metabolism and reduced stress on biological systems, some organisms live for extended periods, their lives unfolding over spans that would seem prolonged elsewhere. This extended duration compensates for the slow pace of growth and reproduction, allowing populations to persist even when individual development takes time. The environment itself reinforces this pattern. Without rapid changes in light or temperature, there are few external signals that would require quick adaptation. Conditions remain stable, providing a consistent backdrop against which slow processes can continue uninterrupted. This stability supports a mode of existence where speed offers little advantage. Over time, this approach becomes embedded in the structure of life at this depth. Bodies, behaviors, and internal systems all align with a pace that matches the availability of resources. There is no excess, no unnecessary acceleration, only a steady progression that allows survival to continue within narrow limits. In this way, slowness is not a constraint, but a solution. It allows organisms to exist within an environment where energy is scarce and opportunities are uncertain. By reducing the need for rapid action, life extends itself across time, moving forward in small, consistent steps that sustain it within the quiet, unchanging darkness. From far above, something begins to fall, though it never gathers into a single form. It descends in fragments, small and scattered, each piece moving at its own pace, drifting through layers of water that slow its passage. There is no single source that can be pointed to, no moment when it begins clearly. It forms continuously, created by processes unfolding at the surface, then released into the depths in a steady, quiet flow. This is often called marine snow, though it does not resemble snow in shape or temperature. It is a mixture of organic material, tiny particles that originate from life above, including fragments of plants, microscopic organisms, waste, and remains that have broken apart over time. Each particle is small, often barely visible, yet together they form a constant descent that connects the surface to the deep. As these particles fall, they change. Bacteria attach to them, breaking down components and altering their composition. Small organisms intercept them, consuming portions and leaving behind what remains. The particles may clump together or separate, their paths shifting slightly as currents guide them downward. By the time they reach greater depths, they have been transformed many times, carrying with them only a fraction of their original energy. Despite this loss, the flow continues without interruption. It is not abundant, but it is persistent. At any given moment, somewhere above, new material is beginning its descent, replacing what has already been consumed or settled. This continuity provides a baseline source of energy, one that does not arrive in large quantities, but does not cease entirely. For many organisms, this falling material forms the foundation of survival. It is collected, filtered, or intercepted as it passes, each particle contributing a small amount of energy that can be used or stored. Feeding in this way does not involve pursuit or sudden action, but a steady interaction with what the environment provides. The organism remains in place or moves slowly, allowing the descent to bring resources within reach. This method of feeding requires adaptation to low concentration. Structures that capture particles must be efficient, able to gather material without expending significant energy. Surfaces may be extended or shaped to increase contact, while internal systems process what is collected with minimal loss. Every fragment becomes valuable, contributing to the overall balance that sustains life. The dependence on this falling material links the deep directly to the surface. Without the processes occurring above, the supply would diminish, leaving even fewer resources available below. The deep does not generate this input independently. It receives what is produced elsewhere, relying on a connection that spans the entire column of the ocean. This connection is not immediate. The journey from surface to depth can take days or longer, depending on the size and composition of the particles. During that time, much of the original material is consumed or altered, reducing the amount that ultimately arrives. What reaches the deepest regions is therefore limited, both in quantity and in energy content. Even so, this steady descent shapes the entire system. It provides a background level of nourishment that supports a wide range of organisms, from the smallest to those that depend indirectly on this source. The flow is gentle, almost imperceptible, yet it remains essential. Within the darkness, this quiet rain continues without pause. It does not draw attention, nor does it change rapidly. It simply falls, carrying with it the remnants of life above, sustaining a world that exists far below, connected through a constant exchange that moves silently through the water. At rare intervals, the steady descent of small particles is interrupted by something far larger. A body begins its fall from the surface, massive and intact, carrying with it a concentrated store of energy, unlike anything that usually reaches these depths. It moves downward slowly, guided by gravity alone, passing through layers where smaller fragments drift continuously. As it descends, parts may break away, but the majority remains whole, continuing until it reaches the seafloor. When it arrives, the change is immediate. What was once a quiet expanse becomes the center of activity. The presence of such a large source of organic material alters the balance of the surrounding environment, drawing organisms from the nearby region. Detection occurs through chemical signals released into the water, spreading outward and announcing the arrival without sound or light. Among the most significant of these events are whale falls. The body of a whale, having completed its life at the surface, becomes a resource that can sustain deep-sea communities for extended periods. Its size and composition provide a level of abundance rarely encountered, transforming the area around it into a temporary site of concentrated activity. The first arrivals are often mobile scavengers, organisms capable of reaching the site relatively quickly. They gather along the surface of the body, consuming the soft tissues with efficiency. Feeding occurs continuously, with little pause, as each organism takes advantage of the sudden availability. The scale of the resource allows many to feed at once, though competition remains present, shaped by proximity and access. As the initial layers are consumed, the structure of the remains begins to change. Bones become exposed, and smaller organisms move in, taking advantage of what has been left behind. Some specialize in breaking down these more resilient components, extracting nutrients that are not immediately accessible. Over time, a sequence of communities forms, each one adapted to a different stage of the decomposition process. Bacteria play a central role in this transformation. Within the bones, chemical processes begin to release compounds that support further life. These processes create localized environments where organisms can thrive even after the more visible material has been consumed. The site continues to provide energy, though in different forms, extending its influence over a longer period. During the earlier stages, when soft tissue is still abundant, the rate of consumption is high. Organisms feed rapidly, not out of excess, but because the opportunity is temporary. What has arrived will not remain unchanged. Each moment reduces the available material, and so feeding becomes continuous, with little delay between action and response. Despite the abundance, there is no lasting stability. The resource diminishes steadily, transformed through consumption and decomposition. What begins as a single large presence gradually disperses into smaller components, returning to the surrounding environment in altered forms. As the process continues, the number of organisms at the site begins to decrease. The intensity of activity lessens, and the area slowly returns to its previous state. What remains is a reduced structure, sometimes only the bones, and eventually even these are broken down or buried by sediment. The memory of the event persists only in its effects, the redistribution of energy that briefly altered the balance of the deep. For a time, the environment supported a level of activity that is otherwise rare, shaped by a single descent from far above. In this way, the deep receives occasional moments of abundance, each one limited in duration, yet significant in impact, sustaining life through intervals that stand apart from the steady, minimal flow that defines most of its existence. Across this vast depth, distance defines almost every interaction. Individuals are spread thinly through the water, separated by space that often extends far beyond immediate reach. Movement does not frequently bring one organism into contact with another of its own kind, and even when it does, the encounter may be brief, shaped by currents and drifting paths that do not easily align again. Within this separation, reproduction becomes one of the most uncertain processes of all. Finding a mate is not simply a matter of seeking, but of chance and timing. Without stable pathways or consistent proximity, two individuals must cross paths within a narrow window, each one prepared for an event that may not occur again for a long time. The difficulty lies not only in locating another organism, but in recognizing it and responding before the opportunity passes. Signals help bridge this distance, though they are often subtle. Chemical cues released into the water can travel outward, forming gradients that indicate presence. These signals persist longer than movement alone, allowing others to detect them across wider areas. Following such cues requires sensitivity and patience, as the path is not direct, but shaped by currents that disperse and distort the signal over time. Light can also play a role, used in specific patterns that differ from those associated with feeding or defense. These displays are not constant, but timed carefully, conserving energy while increasing the likelihood of being noticed by others of the same species. Even so, the vastness of the environment means that such signals may go unanswered, fading into the surrounding space without effect. To compensate for this uncertainty, some organisms have developed adaptations that ensure reproduction even when encounters are rare. One approach involves producing a large number of reproductive cells, increasing the probability that some will meet under the right conditions. These cells are released into the water, carried by currents, where they may encounter those from another individual. This method does not require direct contact, relying instead on the movement of the environment to bring elements together. Other adaptations focus on maximizing the success of a single encounter. When two individuals do meet, the process may occur quickly and efficiently, minimizing the chance that separation will occur before reproduction is complete. Structures and behaviors are aligned to facilitate this moment, ensuring that the opportunity is not lost once it arises. There are also strategies that extend the presence of reproductive material beyond the immediate moment. Some organisms can store or retain reproductive cells, allowing them to use them later when conditions become favorable. This ability reduces dependence on simultaneous encounters, providing flexibility within an otherwise unpredictable system. The low density of life at this depth shapes all of these adaptations. With fewer individuals present in a given volume of water, the likelihood of contact decreases, and so each species must operate within this limitation. The solutions vary, but they all address the same underlying challenge, ensuring that reproduction can occur despite the absence of frequent interaction. Over time, these methods have become integrated into the broader patterns of life in the deep. They do not rely on abundance or proximity, but on efficiency, timing, and the ability to function within uncertainty. Each adaptation reflects a balance between energy use and reproductive success, aligning with the same constraints that shape feeding, movement, and survival. Within this quiet expanse, reproduction continues not through regular encounters, but through strategies that account for distance, ensuring that life persists even when connection is rare. At a certain scale, individuality begins to shift. What might appear as a single organism can, upon closer observation, reveal more than one life joined together, not in passing contact, but in permanent union. This arrangement does not arise from chance alone, but from a precise adaptation shaped by the same difficulty that defines so much of existence here, the challenge of finding another of the same kind. In some species of anglerfish, the difference between male and female is not only in form, but in role. The female grows larger, capable of sustaining herself within the environment, while the male remains comparatively small, carrying a different purpose. His existence is directed toward a single objective, locating a female in a space where encounters are rare. When that meeting occurs, it does not end with separation. The male attaches himself to the female's body, often by biting into her skin. At this stage, the connection is physical, but not yet complete. Over time, the tissues at the point of contact begin to change. Cells from both individuals interact, gradually integrating until the boundary between them becomes less distinct. Blood vessels merge, forming a shared circulatory system. Nutrients flow between the two, no longer confined to a single body. The male's internal structures simplify as this process continues. Organs that are no longer necessary for independent survival diminish or disappear, while those required for reproduction remain functional. What began as two separate organisms becomes a single, interconnected system. The male no longer exists as an independent entity, but as a permanent extension of the female. His role is sustained through this attachment, providing reproductive capability whenever it is needed, without the requirement of locating a mate again. This fusion addresses the uncertainty of encounters in a direct way. Once the connection is established, the problem of distance is resolved for the remainder of their existence. Reproduction no longer depends on timing or repeated contact. It becomes an internal process, integrated into the combined structure of both organisms. The permanence of this arrangement reflects the conditions that shaped it. In an environment where the likelihood of meeting another individual is low, ensuring that a single encounter leads to lasting connection increases the probability of reproductive success. The cost is the loss of independence for the male, but this cost is balanced by the certainty it provides. The integration is not abrupt, but gradual, unfolding over time as the bodies adjust to their new state. The immune systems of both individuals adapt to prevent rejection, allowing tissues to merge without conflict. This level of compatibility requires precise biological coordination developed through generations of adaptation. From the outside, the result appears as a single organism with additional structures attached, but internally, the connection is complete. The flow of nutrients, the exchange of materials, and the shared systems create a unified entity that functions as one. This form of reproduction does not rely on repeated interactions or environmental cues. It transforms a rare event into a permanent solution, aligning with the broader pattern of conserving opportunity whenever it appears. The initial meeting becomes sufficient for an extended period, removing the need for future encounters. In this way, the boundary between one life and another becomes less defined. Two organisms merge into a single system, not through temporary association, but through a lasting integration that reflects the demands of the environment they inhabit. A lifetime here unfolds without urgency. From the earliest stages of development, growth proceeds in measured increments, shaped by the same limitations that govern every other process in this environment. There is no rapid transition from one phase to another, no sudden expansion or acceleration. Instead, change accumulates gradually, each adjustment supported by limited resources that arrive over extended periods. The early forms of many species drift or remain within the water, developing slowly as they gather what little energy becomes available. Progress is not marked by clear milestones, but by subtle shifts that may take years to become apparent. Structures form in sequence, each one emerging only when the conditions allow it, resulting in bodies that reflect a long, continuous process rather than a rapid transformation. This slow development aligns with the broader stability of the environment. Without frequent changes in temperature, light, or external disturbance, there is no pressure to grow quickly in response to shifting conditions. The surroundings remain consistent, providing a steady backdrop that supports gradual progression. Life does not need to rush to adapt because the environment itself changes very little. As organisms mature, this pattern continues. Growth may extend well into later stages of life, with size and form adjusting incrementally over time. There is no defined endpoint that must be reached quickly. Instead, development remains open, shaped by ongoing interaction with the environment and the resources it provides. This extended timeline contributes to longevity. With reduced metabolic rates and limited exposure to rapid fluctuations, many deep-sea species experience fewer stresses that would otherwise shorten their lifespan. Cellular processes operate at a controlled pace, reducing the accumulation of damage over time. The body maintains its function through steady, sustained activity, rather than cycles of intense demand. Reproduction, too, reflects this slower rhythm. It may occur less frequently, aligned with the availability of energy and the rare opportunities for successful encounters. Each reproductive event carries significance, supported by a lifetime of gradual preparation rather than rapid turnover. This approach ensures that the continuation of the species remains consistent, even when individual events are infrequent. The absence of strong environmental variation reinforces this continuity. Without seasonal changes or daily cycles of light, there are fewer external cues to drive rapid shifts in behavior or physiology. The organism exists within a stable framework where long-term consistency replaces short-term fluctuation. This allows life to extend across time without the need for constant adjustment. There is also a balance between longevity and resilience. Living longer does not eliminate risk, but it spreads it across a wider span. The organism does not depend on quick success, but on sustained existence. Each year adds to its presence, allowing it to persist through periods where resources are scarce or conditions remain unchanged. Within this extended timeline, interactions occur at a pace that matches the environment. Encounters, feeding, and movement all align with the slow progression of life, forming a system where time itself becomes a resource. It is not measured in rapid sequences, but in long intervals that support continuity. In this way, growth and longevity become intertwined, shaped by the same constraints and opportunities. Life continues not through speed, but through persistence, unfolding steadily within an environment that offers little change, yet supports existence across spans that extend far beyond what might be expected elsewhere. Sound does not disappear here, but it changes character. It moves through the water with a steadiness that differs from the air above, traveling farther and with less loss, yet arriving without the layered noise that usually accompanies it. There are no winds, no surface motion breaking into constant variation, no overlapping sources filling the space. What remains is a quieter field, where individual sounds stand apart rather than blending together. The water carries vibrations efficiently, allowing even small disturbances to travel considerable distances. Density supports this transmission, guiding sound waves through the environment without the rapid dissipation that occurs in less compact mediums. Yet, despite this capacity, the deep remains largely silent, not because sound cannot travel, but because there is so little producing it. Most organisms here do not rely on sound as a primary means of interaction. Movement is restrained, and the processes that might generate noise are minimized. Without rapid motion or frequent contact between surfaces, the opportunities for creating sound decrease. What might be constant elsewhere becomes rare, each occurrence distinct against the surrounding quiet. When sound does emerge, it often originates from subtle sources. A shift in position, a brief contact with another object, or the internal movement of an organism can create vibrations that extend outward. These sounds are not loud or sustained, but they carry through the water with clarity, reaching beyond their point of origin. The perception of these sounds depends on the ability to detect vibration rather than interpret complex patterns. Organisms sensitive to pressure changes can register these signals, integrating them into their awareness of the environment. The information conveyed is limited, often indicating presence or movement rather than detailed structure, yet it remains valuable within a space where other signals are equally sparse. There are also biological sounds produced deliberately, though they are uncommon. Some species generate low-frequency vibrations, using specialized structures to create signals that travel through the water. These sounds may serve purposes related to communication or orientation, though their use is infrequent compared to other forms of sensing. The energy required to produce them is not negligible, and so they are employed with restraint. The absence of continuous noise creates a different auditory landscape. Without background interference, individual sounds retain their identity, arriving without distortion from competing sources. This clarity allows even faint vibrations to be detected, extending the range at which they can be perceived. The environment becomes one where silence enhances the significance of any sound that occurs. This silence also reflects the broader pattern of conservation. Just as movement is minimized to preserve energy, the production of sound remains limited. There is no advantage in creating constant noise, as it does not contribute directly to survival. Instead, Quiet becomes the default condition, aligning with the restrained activity that defines the deep. The stability of the environment further supports this stillness. Without rapid changes or external disturbances, there is little to disrupt the quiet. The water remains consistent, allowing sound to travel without interruption, yet offering few sources to generate it. This balance results in a space where sound is present in potential, but rarely realized. Within this setting, each vibration carries weight. It is not lost among others, but stands alone, moving outward until it fades. The deep does not remove sound, but it reduces it to its simplest form, a series of isolated events within a field of near constant quiet, where silence remains the most enduring condition. Far above the deepest layers, a slow ascent begins, not from a single point, but across vast stretches of the ocean at once. Countless small bodies rise together, though not in formation, each one guided by internal rhythms that align with the fading of light at the surface. The movement is subtle at first, barely noticeable within the larger stillness, yet it unfolds across such a wide area that it becomes one of the most extensive daily shifts on Earth. This is vertical migration, a pattern in which organisms travel upward during the darker hours and return downward as light reappears. It connects distant layers of the ocean, linking zones that differ in conditions yet remain part of a continuous system. The movement does not occur in a single group, but across many species, each one participating in its own way. The ascent brings these organisms closer to regions where food is more readily available. Nearer the surface, microscopic life forms exist in greater concentration, supported by processes that rely on sunlight. By moving upward under the cover of darkness, migrating species gain access to this abundance, while reducing the risk of being detected. As the surface begins to brighten again, the direction reverses. The same organisms descend, returning to deeper layers where light no longer reaches. This downward movement restores the balance between feeding and safety, allowing them to occupy an environment where visibility is reduced and exposure is limited. The distances involved vary, but they can span hundreds of meters or more within a single cycle. For small organisms, this represents a significant journey, requiring coordination between internal energy reserves and environmental cues. The movement is not rapid, but steady, unfolding over hours as each individual adjusts its position within the water column. Light plays a central role in guiding this pattern, though not in a way that depends on direct visibility. Changes in intensity, even subtle ones, are detected through sensitive structures, allowing organisms to track the transition between day and night. These cues trigger the beginning of ascent or descent, synchronizing movement across large populations without the need for direct interaction. The effect of this migration extends beyond individual survival. As organisms move between layers, they transport energy through the water, carrying what they have consumed upward or downward. This redistribution links different parts of the ocean, creating pathways through which nutrients and organic material are transferred. Predators also respond to this movement, adjusting their own positions to intercept migrating prey. The pattern becomes a dynamic system where multiple species interact across changing depths, each one adapting to the same cycle. The result is a vertical flow of life that rises and falls with the passage of time. Despite its scale, the movement remains quiet. There is no single moment when it begins or ends, no visible boundary that marks its extent. It occurs continuously, distributed across the ocean, unfolding with a consistency that persists day after day. Within the deeper regions, the effects of this migration are felt as subtle changes in presence. At certain times, more organisms pass through, bringing with them the traces of their journey from above. Then they move on, returning to higher layers or continuing downward, leaving the deeper environment as they found it. This daily movement connects distant parts of the ocean in a rhythm that repeats without interruption. It does not alter the stillness of the deep, but it introduces a quiet flow within it, a passage of life that moves between layers, guided by changes that occur far above, yet shape patterns that extend all the way down. There are forms that do not announce themselves through movement at all. They remain in place for such extended periods that their presence becomes indistinguishable from the surrounding space. No drifting, no adjustment, no visible sign that anything is there. Only the quiet persistence of a body held in readiness, aligned with an environment where motion is neither frequent nor required. For these predators, waiting is not a passive state, but the central method by which they survive. They do not move through the water in search of prey, nor do they pursue across distance. Instead, they occupy a position and allow the environment to carry opportunity toward them, relying on the same slow processes that shape everything else at this depth. The stillness they maintain is precise. Muscles remain engaged just enough to hold position, while unnecessary movement is avoided entirely. Even small adjustments are minimized, reducing any disturbance that might reveal their presence. The body becomes a fixed point within the water, indistinct and silent, integrated into the background. Detection occurs through subtle signals that do not require sight. A faint shift in pressure, a slight alteration in the flow, the smallest indication that something is moving nearby. These cues arrive gradually, giving the predator time to interpret direction and distance without needing to respond immediately. Patience defines this approach. Long intervals pass without any change, the organism maintaining its position without indication of activity. There is no urgency to act, no attempt to force an encounter. The predator remains prepared, conserving energy while waiting for the rare moment when conditions align. When that moment arrives, the response is immediate. The transition from stillness to action is brief and controlled, a sudden movement that resolves the encounter within a narrow window of time. There is no extended pursuit, no sustained chase. The action occurs within the space already occupied, using proximity rather than speed to secure the outcome. This method reduces uncertainty. By waiting within a fixed location, the predator ensures that any encounter happens within a known range, where response can be precise. The absence of movement prior to the event also reduces the likelihood of detection, allowing the predator to remain unnoticed until the final moment. The rarity of these encounters does not diminish their importance. Each one carries significant weight, providing energy that must sustain the organism until the next opportunity arises. This reinforces the need for accuracy, ensuring that when action is taken, it leads to a successful result. The body reflects this balance between inactivity and sudden motion. Muscles are adapted for short bursts rather than prolonged effort, capable of generating force quickly, but not designed for extended use. Structures involved in capture are positioned for immediate engagement, requiring minimal adjustment once the signal to act is received. There is also an alignment with the broader stillness of the environment. Without constant movement or noise, the predator's lack of activity does not stand out. It becomes part of the prevailing condition, indistinguishable from the quiet that surrounds it. Over time, this strategy becomes refined, shaped by the constraints of energy and the unpredictability of encounters. It does not rely on speed or endurance, but on timing and precision, allowing life to persist through moments that are few but decisive. Within this depth, where motion is costly and opportunity uncertain, waiting becomes a form of control, a way of aligning with the environment so completely that when change finally occurs, it is met with exact and efficient response. For a long time, the deep was imagined rather than observed. Its existence was known in terms of depth and pressure, measured indirectly through lines lowered into the ocean, but what lived there remained uncertain. Without direct access, assumptions filled the space, often guided by the belief that life could not persist in such conditions. The absence of light, the cold, the immense pressure, all suggested an environment too extreme to support anything beyond the simplest forms. This view began to shift as technology allowed the first deliberate descents into these depths. Early expeditions carried instruments designed to withstand conditions that had once been considered unreachable. Submersibles and reinforced vessels made it possible to approach the deep not just as a concept, but as a place that could be entered and observed. When these early journeys reached the seafloor and the surrounding waters, the expectations carried downward did not match what was found. Instead of emptiness, there was presence, not in overwhelming abundance, but in forms that were clearly adapted, organized, and active within their environment. Creatures appeared that did not resemble those known from shallower regions, their structures shaped by conditions that had rarely been considered in detail. Movement was measured, forms were unusual, and the entire system operated under a different set of constraints than those familiar above. The first reactions to these observations were shaped by both surprise and careful attention. Each new form required interpretation, and without prior examples, classification was not immediate. Structures that seemed unfamiliar had to be understood in terms of their function, and behaviors that did not align with known patterns had to be observed repeatedly before they could be described with confidence. These early encounters also revealed that life in the deep did not depend directly on sunlight. This realization altered a fundamental assumption about how ecosystems function. If energy could be sustained without light, then the range of environments capable of supporting life expanded beyond previous limits. The deep became an example of a system operating independently from the processes that dominate the surface. As more expeditions followed, the picture became clearer, though never complete. Each descent added new observations, refining earlier interpretations and introducing forms that had not been seen before. Patterns began to emerge, showing that the deep was not uniform, but composed of varied regions, each with its own characteristics and communities. The methods used to explore also evolved. Early submersibles provided direct but limited views, constrained by the duration of each descent and the reach of available equipment. Over time, remotely operated vehicles extended this capability, allowing for longer observation and more detailed study without the same limitations. Cameras, sensors, and sampling tools brought back information that could be examined carefully, expanding understanding beyond what could be seen in a single visit. These developments changed scientific understanding in a gradual but significant way. The deep ocean was no longer considered an empty or marginal space, but a complex environment with its own systems, interactions, and adaptations. It became clear that life could exist under conditions far removed from those previously thought necessary, broadening the scope of what was considered possible. Even so, each new discovery emphasized how much remained unknown. The scale of the ocean and the difficulty of accessing its deepest regions meant that exploration could only cover small portions at a time. Observations were detailed, but limited in range, leaving large areas unexamined. What began as a challenge to earlier assumptions grew into a continuing process of discovery. The first glimpses revealed that the deep was not defined by absence, but by forms and systems that required new ways of understanding, shaping a view of life that extended beyond familiar boundaries. The first images brought back from the deep did not always fit into known categories. Forms appeared that seemed incomplete or exaggerated, structures arranged in ways that did not align with familiar patterns. Bodies carried features that looked impractical, proportions that seemed unbalanced, and surfaces that reflected little of what had been seen in other parts of the ocean. Without context, these shapes invited interpretation, and early attempts to understand them often followed expectations formed elsewhere. At times, these interpretations led in uncertain directions. Features that served specific purposes under deep conditions were mistaken for irregularities or distortions. A structure adapted for sensing might be seen as ornamental. A form shaped for energy conservation might be described as underdeveloped. Without direct knowledge of the environment, it was difficult to recognize how these bodies functioned within it. The unfamiliarity extended beyond individual features. Entire organisms appeared to operate under different principles, their behaviors and forms reflecting constraints that had not been fully considered before. What seemed unusual at first often revealed a precise logic when observed more closely, though this required time and repeated encounters. Some creatures were initially thought to be separate species when they were later understood to represent different stages of the same organism. Others appeared so distinct from known forms that their placement within existing classifications became uncertain. The process of identifying and categorizing them required careful study, comparing structures and behaviors across multiple observations to establish relationships that were not immediately clear. Body structures that seemed exaggerated often served highly specific roles. Extended appendages, unusual proportions, and reduced features all reflected adaptations to the conditions of the deep. What might appear excessive or lacking in one context became efficient when considered within the limitations of energy, visibility, and movement that defined the environment. Over time, patterns began to emerge. Similar solutions appeared across different species, each one addressing the same challenges in slightly different ways. These recurring features provided a framework for understanding, allowing scientists to move beyond initial impressions and toward explanations grounded in function. This process gradually reshaped expectations of what life could look like. The idea that organisms would follow a limited set of forms, defined by conditions at the surface, gave way to a broader view. Life could take on structures that seemed unfamiliar, yet remained entirely suited to their environment. The range of possible forms expanded, reflecting the diversity of conditions under which life can persist. As more observations accumulated, earlier misinterpretations were revised. Structures once thought to be unnecessary were recognized as essential. Behaviors that seemed unusual were understood as responses to specific constraints. Each correction added to a more accurate picture, refining the understanding of how life operates in the deep. This shift did not occur all at once, but through a series of adjustments. Each new encounter provided additional detail, allowing previous assumptions to be reconsidered and refined. The process remained ongoing, shaped by the gradual accumulation of knowledge rather than a single moment of realization. In the end, the creatures that did not make sense at first became examples of how limited expectations can be when faced with unfamiliar conditions. Their forms, once difficult to interpret, revealed the extent to which life can adapt, reshaping itself to fit environments that extend far beyond what was initially imagined. Reaching this depth no longer depends on imagination alone, but on machines built to endure conditions that remain beyond direct human exposure. Modern exploration relies on submersibles and remotely operated vehicles, each designed to descend through layers of water while maintaining structural integrity under immense pressure. Their forms are compact and reinforced, with hulls shaped to distribute force evenly, allowing them to move downward without collapsing under the weight that surrounds them. Some of these vessels carry human occupants, enclosed within thick boundaries that separate them from the environment outside. Inside, observation occurs through small viewing ports or through screens that display images captured by external cameras. The descent is controlled, measured carefully to ensure that both the vessel and its occupants remain within safe limits. More often, exploration is conducted through remotely operated systems. These vehicles are connected to a surface vessel by long cables that transmit power and information. They move through the water under precise control, guided by operators who remain far above. Cameras mounted on their exterior provide continuous visual feedback, while mechanical arms allow for interaction with the surroundings, collecting samples or adjusting equipment as needed. Autonomous systems extend this capability further. Programmed in advance, they navigate predetermined paths, recording data over extended periods without direct control. Their movement is guided by internal systems that maintain orientation and depth, allowing them to explore areas that might be difficult to reach otherwise. Despite these advancements, the process remains limited in important ways. The area that can be observed during a single descent is small compared to the vastness of the ocean. Each mission covers only a fraction of the space, leaving much of the environment unvisited. The time available at depth is also constrained, shaped by the endurance of the equipment and the resources required to support it. Visibility presents another challenge. Even with artificial lighting, the field of view remains narrow, revealing only what lies directly within the reach of the cameras. The surrounding space extends beyond this illuminated area, remaining unseen. What is observed is therefore partial, a sequence of moments rather than a continuous view of the entire environment. The presence of the exploration equipment can also influence what is seen. Lights and movement may alter the behavior of nearby organisms, causing them to react in ways that would not occur otherwise. This introduces a layer of interpretation, where observations must account for the interaction between the observer and the observed. Communication between the surface and the vehicles below is subject to delay and limitation. Signals travel through long cables or rely on acoustic transmission, both of which impose constraints on the speed and clarity of information exchange. This affects how quickly adjustments can be made and how data is received. Temperature, pressure, and corrosion further challenge the durability of equipment. Materials must withstand prolonged exposure to conditions that can degrade or weaken them over time. Maintenance and repair become complex, requiring careful preparation before each descent and detailed analysis afterward. Even with these constraints, each exploration adds to a growing understanding. Data collected from sensors, images captured by cameras, and samples brought back to the surface contribute to a more detailed picture of the deep. Patterns begin to form, linking observations across different regions and times. The process remains gradual, shaped by both technological capability and the inherent difficulty of the environment. Exploration does not proceed continuously, but in measured steps, each one extending knowledge slightly further. The deep remains largely beyond direct reach, yet through these methods, it becomes increasingly accessible, revealing its details piece by piece without ever becoming fully known. Beyond the edges of every recorded observation, the ocean continues without interruption. What has been seen forms only a narrow record, a collection of moments gathered from specific places and times, each one precise yet limited in reach. Outside those brief windows, the environment extends in all directions, carrying forms and processes that remain unobserved. The absence of data in these regions does not indicate absence of life, but rather the boundaries of what has been accessed. Estimates suggest that a large portion of deep-sea species have not yet been described. This conclusion arises from patterns already observed, where each new exploration tends to reveal organisms that were previously unknown. The rate at which unfamiliar forms appear indicates that the catalog of life is incomplete, shaped more by opportunity to observe than by the total number of existing species. The structure of the ocean contributes to this uncertainty. It is not a single continuous space that can be surveyed in full, but a layered and varied system with differences in depth, terrain, and chemical composition. Each region may support distinct communities, adapted to local conditions that are not replicated elsewhere. Exploring one area provides insight into that specific environment, but does not fully represent the others. Physical access remains one of the primary limitations. Reaching extreme depths requires equipment that can withstand pressures far beyond those encountered at the surface. Even with modern technology, each descent involves preparation, resources, and time, restricting how frequently these missions can occur. The number of accessible sites remains small compared to the total area of the deep ocean. Time itself becomes a limiting factor. Observations are often brief, capturing only a small segment of ongoing processes. Many events unfold slowly or infrequently, making them difficult to document within the duration of a single expedition. As a result, understanding is built from fragments, assembled gradually as more data becomes available. There is also the challenge of detection. Some organisms remain difficult to observe, even when present, either because they occupy spaces beyond the immediate field of view, or because their forms do not reflect available light in ways that make them easily visible. The absence of observation may reflect the limits of current methods rather than the absence of the organisms themselves. Sampling introduces additional constraints. Collecting physical specimens can alter delicate structures or fail to capture behaviors that only occur in their natural setting. While samples provide valuable information, they represent only one aspect of a broader system that cannot be fully preserved outside its environment. The scale of what remains unseen is therefore not defined by a single measurement, but by the combination of these limitations. Each one restricts access in a different way, shaping a view that is detailed in places yet incomplete overall. The known and the unknown exist together, separated not by clear boundaries, but by the extent of exploration achieved so far. Despite this, the process continues, guided by the understanding that each new observation contributes to a larger picture. Patterns become clearer as more data is gathered, and relationships between species and environments begin to emerge. Still, the deep retains much of its complexity, with vast regions remaining beyond direct observation. What lies within those regions is not entirely unpredictable, but neither is it fully understood. The deep ocean remains an environment where discovery is ongoing, where the number of known forms continues to grow, and where the majority of what exists has yet to be observed in detail, extending the boundaries of knowledge without reaching a final edge. It continues without needing to be seen. Far below the reach of sunlight, Life persists in a steady, unbroken flow, sustained by processes that do not depend on the surface. There is no daily cycle of brightness and darkness to guide it, no shifting patterns of light to mark the passage of time. Instead, continuity replaces change, and existence unfolds within a narrow range of conditions that remain stable over long periods. Energy moves through this environment in ways that differ from those above. It arrives indirectly, carried downward through drifting material, or generated through chemical interactions that occur within the water and along the seafloor. These sources do not produce abundance, but they provide enough to maintain a system that operates with careful balance. Organisms here are shaped by this limited supply. Their structures, behaviors, and rhythms align with an environment where energy is neither constant nor plentiful, but sufficient when used with precision. Growth proceeds slowly, interactions occur infrequently, and survival depends on conserving what is available rather than seeking more. This independence from sunlight alters the structure of the ecosystem. While connections to the surface remain through the gradual movement of material, the deep does not rely directly on processes driven by light. It functions as a system that can continue even in the absence of immediate input from above, maintaining its own internal balance through the interactions of its inhabitants. The absence of light also removes certain constraints. Without visibility as a primary factor, forms and behaviors evolve in response to other conditions, such as pressure, temperature, and the availability of energy. The result is a range of adaptations that reflect the priorities of this environment rather than those of the surface world. Time itself takes on a different character. Without the regular alternation of day and night, cycles become less defined and processes unfold at their own pace. The environment remains consistent, allowing life to proceed without the interruptions or fluctuations that occur elsewhere. Stability replaces variation, creating a setting where gradual change is more common than sudden shifts. Within this quiet continuity, interactions remain subtle. Encounters occur, energy is transferred, and life continues, yet these events are distributed across time in a way that avoids concentration. There are no moments of widespread activity, no peaks that define the system. Instead, everything proceeds at a steady, measured pace. This does not make the environment simple. The relationships between organisms, the movement of energy, and the adaptations that sustain life form a network that is complex in its own way. It is not driven by intensity, but by persistence, where each component contributes to a balance that remains intact over long periods. Much of this system remains beyond direct observation. The limits of exploration leave large areas unexamined, and many processes continue without being recorded. What is known provides insight into how life can exist under these conditions, yet it also highlights how much remains unobserved. The deep ocean stands as a reminder of this scale. It shows that life can persist in ways that do not align with familiar patterns, extending into environments that operate under different rules. It reveals a continuity that does not depend on light, a system that remains active even when unseen. And within that continuity, there is no clear boundary where understanding ends and uncertainty begins. The known and the unknown exist together, shaped by the extent of observation and the vastness that remains beyond it, where life continues quietly, following patterns that are only partly understood.